Okay, everyone, your last lecture. Okay, now today in the program, I just want to discuss very briefly two types of catalysis that we sort of haven't discussed, although someone did give a lecture on hydroacylation, so we've already been introduced. I'm going to discuss these two topics in a very superficial way. I just want you to sort of have seen it, basically, so that we have really a complete series of catalytic transformations. But before I get there, I just want to revisit very briefly what we were discussing last week about asymmetric hydrogenations. Now remember, we discussed pretty much in a lot of detail Knowles' synthesis of L-DOPA. Remember, and we said if you start with the chiral catalyst like this is rhodium dipam. A chiral enamide, or prochiral enamide, can approach in two ways, from the Re or the C phase, or the psi phase, and depending on the steric demand in the catalyst, it will approach from one side or the other. Now, we looked at the so-called quadrant argument of Knowles, you might recall. So the quadrant diagram for this rhodium dipam catalyst would be something like this, where we shade the quadrants that exhibit steric demand. And we get this from the X-ray structure of the complex. So this is now the catalyst precursor, essentially, remember? The complex that he employed, or that one can employ, is rhodium RR dipam, cyclooxidine plus. It loses cyclooxidine and you generate this species here. And the dipam has these O-methoxy groups here shown in green. Now, you might recall that the prochiral alkene can either approach from this face or from this face. Clearly, approach from this face is more preferential because if we look at the quadrants, the sterically demanding groups, i.e. this carboxylic acid group, is in a quadrant that has no steric demand. So it approaches this way. Now, what I glossed over last week was what happens next. So I want to just look at what happens after the coordination. That's going to ultimately predict the stereochemistry of the product. But let's just see what happens next. So it approaches from this direction. Remember, the ketone also coordinates. And the very first step after the approach is coordination. Right? So you've got a square planar rhodium complex, right? And you've approached from the preferential face of the alkene. So you end up with a square planar coordination complex. Does everyone see that? The ketone is coordinated as well, and the alkene is coordinated. Okay? Now what happens next, of course, is what? In the second step. Well, in the next step. What happens in the next step is hydrogen activation. So of course this complex now, this intermediate, is how many valence electrons? 16. So it undergoes oxidative addition with hydrogen. Now I'm just going to remove the alkene for a moment. The hydrogen is going to attack, and we're going to have cis coordination, because remember it occurs in a concerted fashion, and we're going to end up with a cis dihydride. Remember, hydrogen activation and hydrogenation proceeds via what? Sort of an intermediate. Sigma, a sigma dihydrogen complex. Alright, so there it is. And now what actually happens is the ketone, which was coordinated like this, or this enamide, what actually basically happens now is the following. Just to show you, the ketone oxygen actually coordinates at the bottom because we've now displaced the position where the ketone was sitting for the dihydrogen. And it's a weak coordination because it's just the lone pair on the oxygen is coordinating. So it goes and sits at the bottom of the octahedron. Check it out. You see that? And we have the coordinated alkene over. So it's a bit difficult to view, but these rings are flat. So something like that. It looks a bit congested, but you can see that it's going to form an intermediate that looks like this with a ketone at the bottom. And now the key step. This hydrogen, check it out guys, this hydrogen is going to hop over here, right? You see that the green hydrogen is going to go to this carbon, and this green hydrogen is going to go to this carbon. And we're going to get sort of, we're going to get a reductive elimination, essentially, and decoordination. But do you see that this, because of the way that this guy is oriented, this hydrogen atom will go, sit on the carbon in this orientation here, when it decoordinates. Not this way, but this way. And that's how you get the right stereochemistry at this carbon. If it had approached from the other direction, of course you'd get the other enantiomer. So that's really the whole mechanism. And just remember, the mechanism of these asymmetric hydrogenations employing these typical rhodium complexes occurs slightly differently to the rhodium tris-triphenylphosphine complex of old Wilkinson. Remember? So with Wilkinson you get the hydrogen activation first, then the alkene coordination. In this case you get the alkene / ketone or enamide coordination first, then dihydrogen activation. Are there any questions? I know the model looks pretty congested, but what it boils down to is this, right? So remember this is a very convincing way that you can see how things approach. Right, what I want us to talk about today, very briefly, is hydrocyanation and hydrosylation. Now I'm going to touch on this very briefly because I don't think that it's important for us to kill ourselves with details. But hydrocyanation is an important industrial process where essentially you attach or you add an HCN, hydrogen cyanide gas, over a CC double bond. This is an important process industrially. It's employed by DuPont, which is a chemical company in the United States, in the synthesis of something called adiponitrile. This is the structure of adiponitrile from butadiene. So butadiene is a readily available industrial feedstock, and using this process of catalytic hydrocyanation, you can convert it to adiponitrile. Now this, in turn, is a very important and useful starting material, in fact, in the synthesis of nylon 6,6, because you can readily convert a CN group to a carboxylic acid group. How do we do that? Organic chemistry 101.
Yes, CN.
You react it, you essentially just acidify it. That's one way of doing it. And how do we put an AN group on here? You do a reduction of the CN. Anyway, it's very possible, it's easy to convert these two groups here. They're great synthetic groups in organic chemistry for functionalization. And you can get adipic acid and hexamethylene diene. This is of course got 6 carbon atoms. This has got 6 carbon atoms. But yeah, you see what you can basically do, because you start off with a 4 carbon center and you add 2 equivalents effectively of hydrogen cyanide, so you get a 6 carbon chain, and that can be converted to these 2 products, which are the starting materials in the synthesis of nylon. Okay, so what you basically then do is you do a condensation, very similar to the sorts of condensations you get in the synthesis of amino acids, right? So you form an amide functionality and basically it polymerizes and you get nylon. Now, this is a very interesting reaction. Of course, you start off with a butadiene, which has got 2 CC double bonds. So you've got to in fact do this so-called hydrocyanation reaction twice over the ECC double bonds. Now, this is the catalyst cycle of the process from these two guys, McKinney and Rowe, who both worked at DuPont. And it's catalyzed effectively by a nickel zero precursor, and L in this case are so-called phosphite ligands. Let me write that down. So for hydrocyanation, we employ nickel together with typically and traditionally phosphite ligands. Now, what is a phosphite ligand? We know what a phosphine ligand is. PR3, what is phosphite?
Oxygen.
Correct. That is a phosphite ligand. Now, what essentially happens, and this is actually quite an interesting mechanism, and it's been studied using stoichiometric reactions, low temperature NMR experiments, and so on. By the way, where's Julia today?
Oh, she's not coming.
Okay, she all right?
Yeah.
Oh, she's got a presentation
Yeah.
today.
Then she went to finish.
So that's the starting material. Two phosphite ligands which are neutral, nickel zero, and a coordinated alkene. Let's start at that point in the cycle there. Now that's reminiscent of Zeiss's salt, right? It's an alkene complex. How many valence electrons does that complex have? Correct, 16. It's a 16 valence electron complex. So it sees HCN gas, which is floating around in the reactor, and we have an oxidative addition reaction. We now have how many valence electrons? Correct, 18. Now this process has been, as I said, studied very carefully during low temperature NMR experiments and so on, in situ studies, particularly by McKinney and Rowe. What happens at this stage is the 18 valence electron olefin complex then essentially uses one of the phosphites, and you end up with this square planar complex here, which is of course 16 valence electrons. And what you then actually have is two things happening simultaneously. Coordination of an olefin, right, and insertion of the olefin into the nickel hydride. So you have an insertion and coordination. So you end up with this square planar complex here, this intermediate, which is an alkyl olefin complex. And what happens now is, of course, this guy here is hungry for electrons. It's electron deficient, so the ligand, the phosphite, recoordinates. You get a 5 coordinate intermediate, and then you get reductive elimination. Now I've skipped a step here. What step have I skipped in this reductive elimination step?
Isomerization.
Correct. It has to undergo isomerization. Why? Because they have to be mutually cis. Very good. Here they represent a trans. Now, just a sort of a side remark on that. That's not a problem, typically, in 5 coordinate transition metal complexes like this, because you have something which I might have mentioned before called Berry pseudo-rotation. So Berry pseudo-rotation is simply where axial and equatorial groups exchange rapidly, and they interchange between trigonal bipyramidal systems via square pyramidal transition states. So you can imagine a simple way to imagine Berry pseudo-rotation is in fact that basically the axial and the equatorial groups exchange rapidly, and the axial and the equatorial groups here exchange rapidly on an NMR time scale. Just exchanging rapidly on any time scale. And then, of course, if this guy over here goes and sits in this equatorial position here, and this CN goes and sits in this equatorial position here, they're going to be mutually cis to each other, and then it can reductively eliminate. And then what I'm going to be left with essentially is the three-coordinate product again, right? Which might then undergo some sort of a rebalancing essentially to form this trigonal planar intermediate. Yes.
So there's not a set step of isomerization. It's just always doing it from this Berry.
That's a very good question. You know, Berry pseudorotation is a process that is highly dependent on various factors, electronic and steric. Depending on the size of these substituents, the Berry pseudorotation will be retarded. That's the first thing. And the second thing is it also depends on the electronic characteristics of this guy here. Now, so it's highly dependent, but generally, if you have a 5-coordinate system, the rule of thumb is that it undergoes Berry pseudorotation rapidly. Sometimes you can freeze out that Berry pseudorotation. So if you have very large substituents here, you know, you can actually slow down the process, or you can cool it down to low temperatures, and then actually you can sort of freeze it out. It's even possible in some cases, I mean, I've managed to do this in my own work, to trap the square pyramidal intermediate, right, which is very rare. Very difficult to that's generally the high energy thing. So I'm sort of digressing a bit, but to go from this 5-coordinate system back to the 3-coordinate system, there is a Berry pseudorotation, mutually cis groups, and reductive elimination to form the product. Now, this step here involving pseudorotation, okay, involving pseudorotation as an isomerization step, if you will, is going to, as I just said, be dependent on the nature of the ligands, right? So that's going to be an important thing in designing the ligand that you employ. All right, but that's basically the catalyst cycle. And what I'd like to say about this is industrially, and in the DuPont process, you start with butadiene. So what you basically have is you form a hydrocyanated intermediate 1 via one of these cycles. And then, of course, that alkene will go into another cycle, essentially, and you will get the adiponitrile product. There are some issues with selectivity in the reaction industrially. So what you often have is you have the formation of, you have some isomerization taking place over the nickel, because it turns out that something we haven't discussed is very often you can do isomerization of CC double bonds over a metal center. In other words, if you have an internal olefin, you can sort of make it move around after it's coordinated to the metal, and that's what happens in this reaction. But that's not a problem, because you end up basically taking, what they do is they take a mixture of these isomers, and over time, basically, you can there's a high selectivity towards the adiponitrile product. So alkene isomerization, I'll just mention that as sort of a throwaway line. Alkene isomerization is an issue in hydrocyanation. Okay. So that's the story. Now, what I wanted to talk about now, so we're now going to shift gears, that's hydrocyanation done and dusted. I want us to talk about hydrocyanation. But before I get to hydrocyanation, I want to mention a very important process, the synthesis of silicones, right? Silicones are, of course, very important. I mean, everyone uses them, particularly as sealants, right? They're very important products, and in fact, there is a company in Germany called Wacker in southern Germany that earns their bread and butter. That's just one example of many companies that comes to mind, making silicones. Now, how does this process work? I thought I'd mention this in the context of hydrocyanation. the process is very interesting. The way that it's made, partially, is called the Muller-Rotchow synthesis. And what you do is you take elemental silicon, you react it with methyl chloride, a copper catalyst at 300 degrees centigrade, and you get a mixture of chlorosilanes. Now, this is a heterogeneous process, right? So imagine you have just copper, you have elemental silicon, and somehow the copper mediates the activation of the carbon-chlorine bond in this molecule, and it is incorporated into the silicon. And we form a mixture of products. Now, these products are not all so useful. The one that is in fact used in the synthesis of silicone is this guy here, dichlorodimethylsilane. And what one does, via distillation, you can purify this mixture that is generated from this Muller-Rotchow synthesis, and you can isolate that, and if you basically hydrolyze it, if you do a careful hydrolysis of that guy, you basically get silicone, right? It proceeds via a silane diol. In other words, if you imagine doing a hydrolysis of this guy, the dichlorodimethylsilane, it forms this intermediate here, and HCl gas is liberated from that step. That HCl gas is in turn, it's not wasted, it is used to regenerate this guy here. So if you take methanol and you react it with HCl, you're going to get chloromethane. We saw something very similar happening, recall, in the one of those carbonylation reactions, the Cativa process, and the Monsanto acetic acid process, where you generate methanol and it reacts with hydrogen iodide, and remember, you get that exchange. That's basically what happens here. If you take methanol, you bubble HCl through it, so it's a cyclical process. The HCl that's generated is then refeeded into the process to form basically chloromethane, which then reacts with silicon mediated by this copper catalyst, and so you can make silicone. Now, the fundamental process, I should mention, going on in this Rotchow synthesis is very interesting from a fundamental perspective, because this process is as old as the hills and has been used since time immemorial, but scientists always speculated what the mechanism of the reaction was. And of course, it's very tempting to say, well, if you start with silicone 0, you're ending up with silicone 4. How can one visualize what's going on there? Well, intuitively, it's kind of like an oxidative addition, isn't it? You kind of have, it appears, some sort of an oxidative addition reaction, if you will. I mean, we talk about oxidative addition in the realm typically of organometallic chemistry, but to go from silicon 0 to silicon plus 4, it looks like we've had 2 successive oxidative addition reactions of something like this over the silicon. And that's not so unreasonable, because, of course, we have silicon 0, and we have CH3I, or sorry, Cl. This bond is highly polarized, so it's conceivable that that some sort of a bond activation process can take place here, forming something like this. That would be an intermediate. Now that intermediate is in fact silicon plus 2, isn't it? And silicon 2 was, up until very recently, about 1986, a completely inaccessible oxidation state. So this was a purported intermediate, something like this, in the synthesis, but it was only recently shown, well, not that recently, about exactly 30 years ago, that this is in fact an accessible oxidation state for silicon. Up until that point, people had only didn't really have any experimental evidence in terms of isolating something that was in a divalent state. And of course, what you can imagine now, this hot intermediate here, which we call a silane, could then, in a second step, react again with another equivalent of methyl chloride, in fact, to form the desired product. So I think that's quite an interesting and industrially important process involving some very interesting silicon chemistry, and it's a heterogeneous process. So that's silicon.
I have a question. What's the ratio of the different products? Because, I mean, would this mechanism explain the other products as well?
I don't know what the ratio is off the top of my head. What I do know is that these other products are not that prevalent. So this is the major product. It is the major product.
Okay.
But yeah, this mechanism here, certainly you're right, explains formation of this product. How we would get to something like this, that would have to be by some sort of a recombination mechanism or some disproportionation. In other words, you can imagine if this guy somehow undergoes decomposition at these temperatures, maybe on the surface, back to that you can have some sort of a reductive elimination. So yeah, I mean, the mechanism I present explains selectivity towards that product, but those are also formed in the reaction by other mechanisms. But you have to do a distillation. If you look at a lot of textbooks, they just say that if you react these two, you get that, but there are other products. So obviously it's formed in high enough quantities that warrants purification.
So the silicon is then in +4 of the liquid.
Correct. It's +4, and then it's +4, +4, +4. It stays +4. In silicone, it's +4 as well. This polymer here. Polydimethylsiloxane is the correct name for silicone. You have a question?
Not really, maybe. So like if yeah, I wasn't. If we press it with a Langmuir Hinchelwood, for example, then we would split both of them, and that would explain why like the majority is the center bit. So like if we decrease the concentration of it, that would be favored as well, right? Maybe.
I think it's difficult to say things like that because you can't predict out of hand. In fact, I'm not sure if it follows the Langmuir Hinchelwood or the.
But that would explain why we have those two, because otherwise they would be like very, very tiny, just trace amounts, right? Maybe.
Well, that's a very good observation. I mean, maybe what happens is you indeed form this guy here, and then that stays adsorbed to the surface, and then undergoes another activation on the copper surface, and then cross-reacts with another activated organic product, something like that.
It's on the copper surface?
It's on a copper surface, yes.
Oh yeah.
So the silicon gets absorbed, this guy gets absorbed. Now I'm not sure if it's a radial mechanism or a Hinchelwood mechanism. I'll have to look that up. But anyway, there's certainly some sort of an activation going on at the surface, and then you form these products. But this with high selectivity towards that one. So silicon 2 is purported to be an intermediate in this very interesting reaction. Okay, now let's talk about hydrosilylation. Now that we've spoken about silicones, which are industrially very relevant, and basically ignore what I have at the bottom of the slide. This is basically in a nutshell hydrosilylation, an example of hydrosilylation. And as we just saw, hydrosilylation means, like we just saw hydrocyanation, we're adding a hydrogen and a silyl group over a carbon-carbon double bond. You also have hydrosilylation, incidentally, of carbon-carbon triple bonds. And, as we will see later in the lecture today, hydrosilylation of carbon-oxygen double bonds, of ketones in particular. This is an example of, we call this trichlorosilane, undergoing a hydrosilylation over this. This is incidentally allyl chloride, right? Allyl chloride. And you form this trichloro species here. Why is hydrosilylation important? Well, it's an exceptionally important process, but I just want to highlight actually this one nice example here, where you can employ hydrosilylation, in fact, to attach catalysts to silica surfaces in a process of adsorption. So, yeah, I mean, to make that guy there, of course, you need to employ hydrosilylation, right, like something like that. And then you can use that as a precursor essentially to fix this ligand onto a silica surface, and then you can attach the catalyst to that, and then you're doing what? You're bridging the gap between homo and heterogeneous catalysis, something very popular in contemporary chemistry. Yeah.
So essentially, hydrosilylation is used in like column chemistry. I mean, to make all your columns, like in HPLC and stuff.
It's used for many things. It's used for, it has many uses indeed. Yes, those are one of the uses, cross-linking polymers and stuff like that. It's got innumerable uses, but basically it is a way to saturate a carbon-carbon double bond, because once you've actually installed a sinyl group here, it's like a synthetic handle. You can do things with it. You can hydrolyze it to an alcohol. You can use it as a leaving group. You can do all sorts of synthetic transformations with it. So it's basically taking something, an alkene, and converting it to a higher product, a higher value product. Alkenes are typically quite inexpensive. You do the hydrosilylation and you get something that's much more amenable to synthetic modifications. That's the point. Now this is actually a very nice example, and in fact I happen to know a guy that did his whole PhD on this, actually from my Cape Town days. His name was Matthew Overett, and he made sinyl dendrimers. And the way that he made it, because we've seen dendrimers before, haven't we, is, and this is actually just from the Departments of Useless Information, how one can build up a dendrimer. This is called a carbosilane dendrimer. You get different types of dendrimers. But you start off with this silane here, so this is tetraallyl silane, and you do a hydrosilylation. So you require a catalyst for that. In other words, the H-SiR3, in this case SiCl3 bond, is not reactive enough that it can just add over the CC double bond. You require a catalyst, and we're going to look at that in a moment. But you basically, in quantitative yields, can isolate this guy here, and then you can actually react that with allyl magnesium bromide and Grignard reagents, and you can basically build up a dendrimer. And the great thing is then what you can do to make a bigger dendrimer is you can do what? You can do it all over again. So at each of these functionalities then, you can build up, essentially do what we did in this step here, and so you grow in an arithmetic progression a dendrimer. And then when it's big enough, you can functionalize it. And why would you want to do that? You'd want to do that because it's a useful material in bridging the gap between homo and heterogeneous catalysis, because you can separate it by ultrafiltration methods. And that was really why people were making dendrimers in the 1990s in particular, because they thought it would solve this problem of removing spent catalyst or catalyst species from the product by using ultrafiltration methods. In other words, very fine membranes that would selectively allow the desired product to pass through but retain the catalyst behind. It wasn't that successful in the end, to my opinion. It was very popular in the 90s, and this is one of the dendrimers that scientists looked at in particular, carbosilane dendrimers, and this is the synthetic strategy that was employed to make them, employing hydrosilylation. Incidentally, there were, again to digress perhaps, there's another type of dendrimer called Hawker-Frichet dendrimers. And these were based on polybenzyl phenyl ether. Basically, they looked something like this. So that would be the first generation dendrimer, and then you can, similar to what we see here, you can in an arithmetic progression build them up. And there were two different types of synthetic strategies. The one was called a convergent synthesis, and the other one a divergent synthesis. Two ways of basically making the dendrimer. So the second generation would look something like this. So you'd, in these positions here, attach this core here, and here as well. And so you can go on and on and on. And because it's an arithmetic growth, in no time at all, by the fourth generation, you have an absolutely humongous dendrimer. But it requires a lot of synthetic work, and it's very tedious to work with and purify. You know, when you get to very large dendrimers, it stops, the selectivity becomes an issue, right?
In the Hawker-Frichet, you have like the different types of connections, maybe?
Let's look at the Hawker-Frichet synthesis, because it's actually very interesting in terms of dendrimers, which we've been sort of discussing. These are the carbocyanine variants, but I'll show you how one builds up a Hawker-Frichet dendrimer, starting from 0. So this is how you do it. It's actually a very clever synthesis. You start off with this guy here. Alright? And what you basically do is you take advantage of the acidity of these H's here, because it's attached to a phenyl ring, and you deprotonate using potassium carbonate. And you add, what you add is this. You add this core. So this we call the core, the dendrimer core. And what we add now is basically the core to the core, if you will. And what's going to happen, we add 2 of those. We're going to get the so-called first generation dendrimer, which is going to look like this. With OHs in these positions. Do you see what's happening? In fact, let me just, I'm running out of space here. But that's what we're going to get. All right? So we've made the dendrimer bigger. Now what you do, watch this. You convert this OH here to a bromine so that it's a better leaving group. You do that by adding carbonate to bromide. There's various ways of doing it. So the next step, you convert that to a bromine. So you get bromine there. That's all we're doing. We're not doing anything else. Sorry, there should be an extra carbonate in here. So don't forget the OHs here. This is the classic Hawker-Frichet synthesis. All right. Now we've built, this is like a first generation dendrimer, it's called. This is called the 0th generation. Now we take this guy here, and what do we do with it? We react this first generation dendrimer with the core again. So what's going to happen now? What's going to happen now is exactly the same sequence is going to take place, but I'm going to end up with a huge, so I'm going to end up with this.
Wouldn't it be more efficient to just react it with the water first generation?
No, because this guy's much bigger. So all of these, this whole wedge here is going to go here and here. So you end up, in the end, having a 7-ring system. Whereas if you just, are you saying, why can't we just react this?
Well, we take one with the bromine and one with only alcohol groups, and we react them together. Because, I mean, because they have more...
Oh, okay, yeah, you're right. You can do that. Yes, that's a possibility. But you can, what you can also do, you can take this guy here, and of course, not react it with us, but with us.
Yeah, that's right.
So yeah, that's right. So this then gets reacted with this, and so now so you're going to have these rings now sitting in these positions. Does everyone see that? And then you're going to get this guy here, which you then convert to the bromine, right? And then you're going to do the same thing again. You're going to then do the phenylation again, but then so yeah, you can play those games, but it's basically, you can see what you're doing. You're building up in an arithmetic progression a larger and larger dendrimer. Just a moment. I just want to check this. So yes. So you react this indeed. You react this with this. This is a good leaving group. And then you get the huge dendrimer, and then you convert the OH to a bromine, and then you do the same thing again and again and again, and you can get very, very large systems. And I think that's actually a very clever and simple way of building up these things, and this is from around 1995, if you're interested, Frichet. That was his key paper. if I remember correctly. Okay, so that's now, we've digressed a bit, but so hydrosylation is something that one can use to build up dendrimers. Now the classic catalysts employed are Speyer, Ludwigs, and Karstedt. These are the three classic hydrosylation catalysts, and they're all based on platinum. In fact, the Speyer catalyst comes from Dow Corning. It was, in fact, discovered there by Speyer. And in fact, it's synthesized by dropping some platinum into aqua regia. Now, platinum actually dissolves, so does gold in aqua regia. Does anyone know what is aqua regia?
Strong acid.
This one uses for the paints, right?
Paints?
It's super strong acid.
Well, it basically dissolves everything. It is nitric acid and hydrochloric acid in a 1:3 ratio. And if you take platinum metal and you drop it into aqua regia, it dissolves. It dissolves exothermically. And what you basically get out of that, according to this reaction, is hexachloroplatinic acid, H2PT-Cl6, and that can be isolated, believe it or not, and that is an active hydrosylation catalyst. Now this is sort of like a second generation Speyer catalyst. All they've actually done is just replace the H2s with tert-butyl amines. That increases the solubility in organic solvents, if you will, of this guy here, so it slightly enhances the catalyst rates. But the Karstedt catalyst is sort of like the big brother of these two, because this is like really a soluble catalyst. You can see it's a platinum 0 olefin complex, and that's the structure of the so-called Karstedt catalyst. And the structure was actually elucidated in the 1990s, 1991, by a guy called Mike Lappert, who was a scientist in Britain who did a lot of very exciting chemistry in the 70s and 80s. I'll write his name down. I think he's passed away. Lappert. He also did a lot of excellent, outstanding, low-valent main group chemistry. But anyway, he was into like isolating reactive hot potatoes, and he got a crystal structure of this guy. Now I just want to show you a video of what happens if you put platinum in aqua regia. Oh no. Okay.
Usually chemical is aqua regia stronger or platinum?
Oh god, I think it was stronger.
What?
We worked with aqua regia.
Really?
In like last year. Was it
Yeah.
last year?
What did you do with aqua regia?
We tried to melt some pig flesh.
Warning, this experiment uses highly corrosive chemical.
I'm sure the pig. I'm sure it's
Yeah.
dissolved.
It turned into goop.
All right, so check this out. That's platinum, pure platinum, and if you drop it in aqua regia, it dissolves. But look at this. I find this really quite interesting. Hydrochloric acid, concentrated. So, look at that. It immediately starts reacting. And
What is that? No, what is it?
It's just a lot of acid.
Wow.
look at that.
So he's making the catalyst now.
Basically, yes. If you dissolve platinum in aqua regia, you make Speyer's catalyst.
There it is.
Yes, there it is. Hexachloroplatinic acid. So that's an acid because it's got acidic protons, so it behaves as a Bronsted acid. Anyway, that's what happens, I think, which is quite amazing. Nice color, but I wouldn't put my finger in that. All right, now, like I said, these catalysts work just fine, but there's also the Karstedt catalyst. The mechanism, we've seen this, somebody gave a presentation, follows, for the most part, yes.
The catalyst, so you keep it in a solution, or do you?
No, you can isolate it. You
Isolate
can
and
isolate
then
it.
you use it.
Yes.
Don't use it.
Yes, because if you take that solution and you add it, it's going to probably destroy everything.
Yeah.
But so and anyway, you don't want to work with aqua regia as a reagent. So what you would do is you'd precipitate it from the solution. And this brown color is, of course, the NO2, right? That's going into solution. You have this NO2 into a 4 equilibrium. Yeah, it can be, but it can be isolated. Now, this is the cycle. This is called the chalk-Harrod mechanism. We start with a platinum 0 species, right? 16 valence electrons, typically, like here, the Karstedt catalyst. And we add the hydrosilane. Now, hydrosilylation, as the name suggests, you need a hydrogen atom on the silicon and 3 other R groups. The rate of the hydrosilylation is going to depend on the nature of those R groups, but you can in principle do it with any R groups, in principle. So you can take, for example, triphenylsilane, trichlorosilane, trimethylsilane. Basically, the choice is yours. So we get an oxidative addition, right, after we have dissociation of ligands to generate a hot potato, right? And in fact, if we started for this species here, how many valence electrons is it? 18. If we lose 2 ligands, how many do we have? 14. And here we're back at 60. So remember, when you're looking at these catalyst cycles, always count electrons, always count d electrons, oxidation states. Platinum 0, that's 10. 4 ligands is 18. Here we have oxidative addition, so it's platinum plus 2, so it's 8. D8 plus 8 is 16. So that's why we can, in fact, as you can see here, well, I mean, platinum square planar platinum complexes of 16 valence electrons in their own right, as we know from simple, yeah, bless you, from simple crystal field theory, are pretty stable. But anyway, we have oxidative addition. We generate this platinum 2 silyl intermediate. That's an interesting compound because it features a metal silicon bond. More about this later. Then we react it with, well, then the alkene comes in. That's going to be hydrosilolated. Here I've used ethylene, but you can use any alkene of your choice. It forms this intermediate here. Now, what does that remind you of? We've seen this before, right at the beginning of our organometallic chemistry classes. Yes? Correct, Zeise's salt. It's very similar structurally to Zeise's salt. It's got the same oxidation state, +2. Okay, remember Zeise's salt was an anionic system, but electronically it's identical. So, I mean, that is for sure a key intermediate in this process, and probably